All right, this is Physics 1C, first hour for October 25th, and today we're talking about magnetism. So this is a kind of brand new topic, and we'll rely on some of the things we've learned before, but there's a lot of new stuff to talk about, so let's get right into it. So magnetism has been known about for a really long time. Your book would have you believe that magnetism was first discovered in a place called Magnesia, which is in western Turkey, or what is modern-day Turkey. And what they early discoveries regarding magnetism were that they found these stones. So they found these stones. They were called lodestones. And what they found was that these stones had the property that they could attract bits of iron. So obviously they knew what iron was by this time. And they found that these lodestones, they didn't know why, but they attracted little tiny pieces of iron. And these things were found on the order of 2,500 years ago. Now, the book explicitly talks about these being found, or this being discovered in Western Turkey, which means it would have been like, well, it's 2,500 years ago. I don't know. My history isn't that good as to who would have been living in Western Turkey at that time. Maybe an ancient Greek civilization or a Hittite civilization or something like that. I don't really remember. Let's see. What is that? 500 years BC? Yeah, maybe the Hittites. I don't really know. Maybe the Greeks. Regardless, some Western civilization knew about lodestones and that they attracted bits of iron. But I know for a fact that these things were known about in ancient China as well, maybe even before that. I think, almost all modern textbooks have a pretty heavy, like, Western slant to them, as in kind of like the history of the white people, so to speak. But the reality is that it certainly wasn't just people in the West that discovered this stuff. Ancient Chinese civilizations knew about this stuff. I'm sure that the Mayans were extremely smart. If they didn't know about magnetism, it maybe would have only been because they just didn't have the right type of stuff around. Because the reality is that these things were kind of rare, these lodestones, and they had no idea how they attracted bits of iron, and they had no idea how to make it better at that process. Nowadays, we call these things just magnets, and you probably have lots of magnets on your fridge. You probably have some magnets inside of some of the electrical components in your computer and things like this, but when we think of a magnet today, normally what we think about is just a bar magnet is usually kind of the way that people think about it, or maybe a horseshoe magnet. These are kind of the two modern versions of magnets. I mean, if you see a magnet in a cartoon, it's probably going to look like a horseshoe. If you see a magnet in a physics lab, it's going to look like a bar magnet like this. So we call this a bar magnet. And magnets have these properties that, just like the lodestones, that they can attract little tiny pieces of iron and other types of metals as well. But iron is a good example. So if you take like a paperclip, for example, and you put it near the end of a magnet here, then it's going to feel a force that is attracted to this end over here. The interesting thing is that iron will also be, so if you have, like, let's say that this is made of iron, right? It's going to be attracted to this end, but if I take a piece of iron, it's also going to be attracted to this end here too, right? So both the north and the south end of a magnet will attract pieces of iron and other types of ferromagnetic materials. There's a lot of different materials that are called ferromagnetic. Some examples are things like nickel and cobalt, nickel being the metal that nickels are made out of, or at least coated in, and then cobalt being another type of metal. These are also things that would be attractive to magnets. You can test this yourself, by the way. If you take a nickel and you put it near one of your magnets on your fridge, I think it'll attract it, although I haven't tried that in a while. Maybe I can try that during the break. Other things that we know about magnets are that if you take a magnet and you put the north end of a magnet, and you take another magnet and you put the north end of that magnet, and you put the north ends together, then what happens? So you try to push these together. Are they going to attract each other, or are they going to repel each other? They're going to repel. So there's going to be a force on this one. There's going to be a force on this one. And what you'll feel is if you take these two magnets and you try to push them together, you'll really feel that there's a force that acts at a distance, and it's very difficult to actually push them together unless the magnet's really weak. When we come into the lab next, which will be next week, I guess, I'll show you guys some really strong magnets called neodymium magnets where when you try to push them together, you feel a gigantic force of repulsion. It's really clear that there's a force there. The opposite of this is if I place the north end of a magnet here and I put it next to the south end of a magnet, then you all probably know that these two magnets are going to feel an attractive force. So in this case, there's going to be a force this way, and there's going to be a force this way. So just like with magnets, just like with electricity, like charges repel, like poles, we call these the poles of the magnet, north and south poles. Like poles of a magnet will repel each other, and opposite poles of a magnet will attract each other. Okay, so these are just some basic things that we know about magnets. Other things that we know about magnets are that if we take a magnet, such as this one that's right here, and we drop little pieces of iron, so they usually call these iron filings, and this is also something that I can show you in the lab. We've got plenty of examples of this that are very easy to show you. It's kind of going off screen, but I think that's okay. So if I put a magnet down like this, and I just sprinkle iron over the top of it like this, what will happen is that a lot of the iron pieces will immediately be attracted to the poles. As you can see, there's a lot of bits of iron that have come here to the poles. But what you also might notice is that the iron itself will kind of line itself up along what you can probably guess are... What do you think's happening here? What is the iron lining up with here, you think? See all the irons kind of like going into the South Pole and kind of going away from North Pole, or vice versa? It's not the electric field. There is no electric field here. It's the magnetic field. So these lines that are created here, if you were to draw smooth lines through here, like for example, if I were to come on here with yellow, and I was to say, okay, it looks like there's a line like this, and it looks like there's a line like that, it looks like there's a line like that. You know, if you kind of just trace through, think of each of these as being a tangent, and you just, what we end up producing is what's called like a dipole magnetic field. So this is the magnetic field. The cool thing about magnets is we can actually see the magnetic field, whereas with the electric field, it's much harder to see. This is easy to do. You can go buy iron filings from like a hardware store, or you could, I guess, create some yourself if you really wanted to. You can buy iron filings. You can buy a magnet very easily, right? And you can just take that magnet, put it on a table. Easiest thing to do is to cover it in paper, so that so you basically you put the magnet and then cover it in paper, and then you just sprinkle iron filings over the top. And that makes it so that the iron filings won't get stuck to the magnet, right? That's the whole point of the paper. And yeah, on the paper itself, you'll just see this perfect distribution, just like this, with a lot of field lines at the poles where the field's the strongest. Right, you see a ton of field lines here. There's a ton of field lines here, right? So the field's clearly the strongest here, because if we think back to the way we talked about electric fields, we said the place where the electric field is the strongest is the place where you have the highest density of field lines, right? Here's another example here to the right where you have a north pole and a south pole that are placed opposite to each other. And look at this one. If you look at the lines here, it should remind you of the lines that are created by an electric dipole. Now you have to understand that electric field lines and magnetic field lines are not the same thing. But they do produce very similar types of arrangements of field lines, okay? But they are different things. They have different units. They are not the same thing, okay? So 3 different examples of magnetic fields produced by bar magnets, okay? Different arrangements of bar magnets. You can get all sorts of different types of magnetic field arrangements depending on how you shape things, and we can actually control very well how magnetic fields are produced. Another thing just to mention, as you probably all know, the Earth itself has a magnetic field. Certainly this is something you've learned about in your life. And the magnetic field of the Earth resembles the magnetic field of a bar magnet. So in this picture right here, what's being shown is here's the Earth, here's a bar magnet that's been situated inside the Earth, and this is more, it's not saying that there's an actual bar magnet inside of our planet, there's not. But there's something that occurs in the core of our planet that we don't fully understand, and it causes the planet to produce a magnetic field. Our planet is not unique in this sense. Other planets also have magnetic fields. Jupiter has a magnetic field, Venus has a magnetic field. I think maybe some planets don't, but I think the majority of them do. Again, this is something where if any of you have been taking astronomy and it's something that's brought up, your astronomy professor told you that it's a mystery why they occur. Mars no longer has a magnetic field. Yeah, I think that sounds right. Yeah, I think that sounds right. Anyway, but the Earth does. Planets do. The Sun has a gigantic magnetic field as well. The Sun's magnetic field is responsible for things like solar flares and at least the shape they take, as well as sunspots. Anyway, so we can imagine that the magnetic field of the Earth is kind of similar to a bar magnet if the south pole of the bar magnet was situated at the north pole of the Earth. I don't know if you can tell here, but this is the North America and this is South America. And then over here would be like Europe, and then at the kind of edge of Africa is right here. So we're imagining that the south pole, the south magnetic pole of the Earth, is at the north geographic pole. It's said right here, south magnetic pole, north geographic pole. And we say that because one of the things that people, and this is going back all the way to like ancient civilizations, one of the things that they learned that they could do with these lodestones was they figured out that if you were to take like a tub of water, right? And in my mind, I imagine that every ancient sailing ship probably was equipped with something like this. And then inside of this, you take your lodestone, so you stick your lodestone inside of this bowl of water so that it's just floating inside the water. I'll answer that question in a second, Cayenne. Then what happens is that this stone, when it's free to rotate, when it floats in the water like this, it will tend to always point in one particular direction. And the direction it will point is toward the North Pole. Now, of course, you need to figure out which direction north is, but the good thing is that ancient sailors knew a lot about astronomy, and even without the use of something like a lodestone to tell them the direction of north, they already knew that they could find the direction of north by looking at the North Star. The magnets allow you to find the direction of north even during the daytime, right? So as long as you figure out where the North Star is and you align your magnet so that it points north, yeah, so what I'm obviously describing here, maybe it's not obvious, is I'm describing how a compass works. So a compass is a little tiny, this will be something we use a lot in this class as a way to measure magnetic fields. A compass is a little tiny magnet that's placed into a vessel that contains usually some kind of liquid like water or something like that, or at least I assume it's water, maybe it's something else, I don't really know. But the point is that the compass is basically just a tiny little magnet. And the north pole of the magnet is here. It's often marked in red. The south pole is often marked in white. And the north pole of this will point toward the north magnetic pole of the Earth. All right, so Cayenne said, doesn't the field have something to do with the magnet turning fast? Possibly. Your guess is as good as mine. If you want to investigate what actually causes the production of the magnetic field of the Earth, this is still a mystery in science. We do not know what it is that's causing the Earth's magnetic field. There are different theories. I'm not going to go into them today. But like I say, if this is something you're really interested in, that's a hotbed of research. Like, doesn't our magnetic pole flip all the time, and will it impact us? Yeah, so my understanding is that over time, the magnetic field of the Earth, the poles will flip over time. I don't know if it's happened during our lifetime. I don't know on what kind of time scales that occurs, but yeah, supposedly that's true, Evan. Yeah. Are lodestones heavy, or is it just a light rock? I don't really know. We have some at the school. I mean, just like any other rock, if we have a big rock, it's going to be heavy. If I have a small rock, it's not going to be that. I mean, it's the same mass as any normal rock that you might pick up. I'll show you one. When we come to school, just remind me to show you one, and I'll show you what a lodestone is. It's literally just a rock, and it will attract, like, nails and stuff. That's all it is. And the really interesting thing is, here's something else, by the way. We don't really know how these were produced either, if I understand correctly. We don't know how lodestones are naturally occurring. We just know that they have magnetic properties. And we're lucky because it allowed these early civilizations to learn about magnetism, so that then later on, when we were trying to figure out what was going on, we could have some kind of there's such a thing as a natural magnet. That's all that a lodestone is, right? Okay, Stefan says there's evidence that it's starting to flip. Yeah, it'd be quite interesting to see what happens if there's any impact on our planet. That was what the question was, right? Will there be some kind of impact on the planet if the poles flip again? I don't really know. Do the field lines go from north to south? They do. Yep. You can see here that this is the North Pole. The field lines come out of north and they go back into south. The north plays kind of like the positive role and the south plays the negative role. Evan says, paleomagnetic records tell us the Earth's magnetic poles have reversed 183 times in the last 83 million years, and at least several hundred times, that's interesting, in the past 160 million years. Okay, so if we take 160, let's say, because that number's easy to use, and we divide by 83, then that means that it happens every 2 million years. Did I do that right? 160 million divided by 83? No, wait. Yeah, 180, call it 160. 160 divided by 80. Yeah, every few million years. So that means that humans haven't even been on this planet for a million years, right? Doesn't our history only go back like 50,000 years? Oof, I probably sound like really stupid if anyone here knows the real number. My point being that probably in the history of human civilization has never flipped. Does that sound accurate, Evan?
I think the calculation was 160 divided by several hundred.
Oh, whatever. It doesn't matter what you do. You're still going to get the same number, roughly. It's going to be every couple million years, right? Regardless, you're saying you wonder why, Evan. Well, I mean, we don't even really know what's causing the magnetic field, right? We say Earth has an iron core, and we think that core is like I'm not going to get caught up in this. We don't know anything about the Earth's magnetic field and why it's produced. We just know that there is one and we can measure it. And often in science, that's all that really matters. The theory of what's actually producing it is probably in the realm of geology and physics, or geophysics, I would guess. And definitely well beyond the scope of this course. Definitely good to think about from time to time, but I mean, I don't know that we're going to have a very fruitful discussion about what's going on until possibly in the next chapter, which will be after this exam, and we learn about what causes magnetism. We're not going to learn about that today. We're just going to learn about magnetism. We're going to talk about what kind of forces it produces. We're going to talk about applications of magnetism, but we're not going to talk about where magnetism comes from today. We're just going to assume that we can go out and buy magnets and we can investigate their properties. Does that make sense? So maybe we can come back to understanding the Earth's magnetic field when we talk about how magnetic fields are produced. All right, Homo erectus has been on Earth for about 2 million years. Yeah, so within the history of human civilization, we would not have experienced a flip. So it'd be really cool if it does happen, we can see what effect that's going to be. I can say one effect that's going to be is going to make that all magnets are now going to point exactly opposite the direction they did before. 42,000 years ago. Okay. That's right around the time the first civilizations were forming. Interesting. I wonder if that has something to do with that. Anyway, okay. So let's talk about magnetic poles and magnetic monopoles, because one of the questions was about, birds will be confused. There are definitely species that geonavigate via magnetism. They use the magnetic field of the Earth to help them navigate directions, stuff like that. So there definitely will be some animals that might be a little bit confused, but I bet you anything they can probably figure it out, and that their internal systems will reorient without a problem, because nature is pretty adaptive. So let's talk about these poles. So I said that you can take a magnet, right? And we can define a bar magnet as having a north pole and a south pole, okay? Now, one of the first questions becomes, so we know that we can produce single electric charges. We can produce single positive charges or single negative charges, right? But if we take a magnet and we cut it in half like this, you might think that what you would get is just on the right-hand side a north pole and just on the right-hand side a south pole. But the truth of the matter is that that's not what happens. When you break a magnet in half, it actually creates two dipoles. So we call each of these a kind of a dipole magnet. It produces a dipole magnetic field. It has a north and it has a south pole, okay? So scientists thought, okay, well maybe if, just because I cut it in half and I get a north and a south pole in between, what if we do it again? So if we cut these again, it turns out that exactly the same thing happens. You end up with a south pole and north pole, a south pole and a north pole, south pole and north pole, south pole and north pole. And we could continue this cutting process down forever. We could even get down to the point that we were left with a single atom. And it would turn out that even with a single atom, okay, a little atom down here, so you've got some atom with its nucleus and it's got its electrons that are flinging around like out here, more than one electron, but let's say that I just draw one of them. It turns out that even a single atom has what's called a dipole moment. And the direction of the magnetic field is going to be this way. So this would be like a bar magnet that's shaped like this. Now, that's not to say that there's a little bar magnet inside of every atom, but every atom acts as if it has a dipole magnetic field, basically is what I'm trying to say. So whether you take a bar and cut it in 2, and 4, and 8 into a million parts, you'll still be left with that many dipole magnets. Am I blocking it a little bit? Yeah, I am. Okay, sorry. So the point is that it is impossible to find a single magnetic pole. At least from what we've seen. So you can't find just a north pole, like a magnetic charge you might think of it as, or just a south pole. You always have a north and a south pole with magnetism. Does that make sense? North and a south pole. And the follow-up of this is that there are no magnetic monopoles. A magnetic monopole would be like a charge for electricity. So we have like an electron, it has a negative charge. We have protons, they have positive charges, right? You might ask, well, does an electron have like a magnetic charge? And the answer is no, it doesn't. Even a single electron acts like a dipole magnet, as it turns out. It has the exact same field as a dipole magnet. Okay? So there's no such thing as a magnetic monopole, as far as we know. There's still a lot of research being done to look for these things. There's all types of experiments that have been designed to try to find magnetic monopoles. There are theories that exist about how they might possibly exist, but we've never found one, and we've been looking for them for at least 150 plus years. That doesn't mean we won't find one. It just means that, as far as we know, they don't exist, and when you cut magnets in half, you're always left with a north and south pole. So can you see how this means that magnetism is going to be quite a bit different than what we learned with electricity? With electricity, most of what we did started from the electric field created by a point charge, right? You know, this is what, literally the first half of this course can kind of be boiled down to this one equation right here. This was the electric field of a point charge, right? And if a magnetic monopole were to exist, if there was such thing as a magnetic charge, then we would start all of this theory that we're talking about right now off with something like this. We would define magnetic force, similar to Coulomb's law. We would define a magnetic field, similar to this, where instead of Q, we would have magnetic charge. You'd probably have like some kind of QM right here. And you'd also have a magnetic field, so this would actually become B. The symbol we use for magnetic field is B. But such a thing doesn't exist, so we can't do this with magnetism. This doesn't work for magnetism. We have to develop magnetism in a different way. And you'll see that. It's the development of magnetism will be very different. The cool thing is that once we finish magnetism and we start to merge electricity and magnetism together, you'll see that there are quite a bit of similarities between the two. Okay, a couple other things to mention. Here. So it's important to understand kind of the history of what we know about magnetism before we go into it, so that once we actually get to those ideas, it'll be somewhat meaningful to you. Well, I didn't leave even remotely enough room here. Move this way down. Okay, so let's mention a couple other things that we know about magnets. So we know that they attract bits of iron. We know that they can repel each other if north puts to north. We know they attract each other when you put north to south. We know that magnetism always comes in these dipole fields. You can have different types of fields, but if you take a dipole magnet and you try to cut it in half, you always get two dipoles, and so on and so forth, so that there are no magnetic monopoles. Another thing we know, and this is really the most kind of important thing for this class, is that if I take an electric wire and it has current that's flowing through it, right? So I take an electric wire here, and I say that it has current flowing in that direction, okay? If I were to take a compass, let's just take the compass that I already drew right here. If I were to take a compass, right, and I were to place the compass on top of my current carrying wire like this right here, okay? Then what would happen is that the compass needle would end up being deflected. I have to think for a second. The compass needle would end up being deflected to the right. And so now I realize that I actually need to draw it like this. So now my compass needle, whoops, I just accidentally got rid of all my... Here. So we got a wire. It has current flowing this way. We place a compass on top of it. So suppose that I label my compass needle so that this is just the direction that it points. I just use a little arrow and say that's the north end of my compass. So if I were to put a compass needle on top of this, what would happen is that it would point off like this. Is that right? Yeah, that's right. The compass needle would actually point this way. Okay? And if I have a current carrying wire that flows down like this, okay, so the current's going down, and now I put a compass on top of it, the compass is going to point, let's see, this way. Okay. So this was discovered by someone named Ørsted. His name is, I think, Hans Christian Ørsted. Is that his name? I didn't write it down. Yeah, Hans Christian Ørsted. But anyway, just Ørsted. In 1820. So this is a really, really important result. The fact that a current-carrying wire will actually deflect a magnetic needle in a compass showed this guy, Ørsted, and anyone else that he shared his work with, that the phenomenon of magnetism is directly connected to the phenomenon of electricity. And that is really, really kind of groundbreaking, where you have something, a magnet that attracts iron, and you have something else, electric current, that lights up light bulbs, and somehow they're connected to each other. So that's a big deal, right? And that was discovered in 1820. And it only took about 30 years after this for Maxwell to write down all of the equations that relate electricity and magnetism. That's where we're going with all this. So this is kind of a history of magnetism. This is all the things we know about it up to this point. And like I said, it's magnets attract iron, magnets repel each other, and current-carrying wires can apparently deflect magnets. Also, the magnetic field of the Earth and these poles and all this kind of thing. Okay. Did Faraday mask magnets? Yes, absolutely. Although he primarily worked with electric current and different types of experiments like that, it's important to understand what magnets do to those systems as well. So he definitely was working with magnetism as well as electromagnets and things like this. Okay, so when we talk about magnetic fields, all right, we need to talk about like units and stuff like that, right? So let's just start talking about magnetic fields. So first of all, the symbol that we use for magnetic field in this class is a capital B. I don't really know why they use B. The units for the magnetic fields are Teslas. And right here I have a list of the size of certain magnetic fields, some approximate magnetic field magnitudes. So let's start with the Earth. The magnetic field of the Earth is 0.5 times 10 to the negative 4 Teslas. Okay? So the magnetic field of the Earth is quite small. At the surface of the Sun, the magnetic field is 10 to the negative 2 Teslas. That's a pretty big magnetic field, but it's still it's the magnetic field of the entire Sun, right? A normal bar magnet has about the same magnetic field strength as the field of the Sun. A strong conventional laboratory magnet, like the neodymium magnets I'm going to show you, are very strong. They have a magnetic field of about 2 Tesla. And then a strong superconducting laboratory magnet would have a field magnitude of something like 30 Tesla. This would be something... Oh, there we go. There's also in here, I skipped over it, a medical MRI unit. You may or may not know that MRI stands for magnetic resonance imaging. Hope I got that right. I believe that's correct. Magnetic resonance imaging. So in order to have that work, you have to have a very strong magnetic fields, and they have magnetic fields on the order of about 1.5 Tesla. So just to give you an idea of what a Tesla is. Okay. Basically, when you think of a bar magnet, that has 0.01 Teslas. Okay. So a normal bar magnet. Is this where Elon Musk got Tesla from? Tesla is a scientist. Nikola Tesla. You should go read about him if you've never heard of him before. He's a scientist from, I want to say Croatia or Serbia. Definitely from that region. It's not important, I guess, but point is that's where he's from. And he was a European scientist that his work on magnetism and electricity was kind of, he was working around the same time as Edison. And as you know, Edison... I'll let you all go into more details about that. But Thomas Edison is kind of famous for being the person that kind of invented the light bulb. I say that in air quotes because I don't know if he really invented it or not. I think he made the first commercially available one, but maybe he invented it. I could be wrong. I don't know. Yeah, so both of them worked in the fields of electricity and magnetism and kind of advanced us into the modern age by creating devices that make our lives easier, like the light bulb, for example. But like Tian Lam is saying, you should absolutely, if you want to know more about who Tesla was, just go read about Nikola Tesla. Go Google it. And as a lot of people are saying, a lot of people believe that Tesla was a lot better than Edison, and there's some evidence for that. One of which being that the way that I don't know how much truth there is to this. I feel like I'm always getting the story wrong, and each time I tell it, I feel like I'm not telling it right. But I believe that Edison, when he was wanting to come up with a way to provide power for all the lights and stuff that they wanted to put in cities and stuff like that, right? So once you know how to make light bulbs, it's a great idea to light up your city at nighttime so that people feel safe walking around. I'm sure none of you would feel safe if you're walking around on our campus if it was late at night and it was very dark. That would be very scary because there could be people lurking in the shadows or whatever. So lighting up the city streets as cities became more and more packed and urbanized during that time was really important. And so you have to think about how are we going to light up our entire city? We're going to have to provide it with electricity. And Edison's idea was that they would use DC power stations that would be planted throughout the city. Think kind of similar to the way that Wi-Fi stations are planted throughout the city now, or actually not Wi-Fi, sorry, cell towers. So Edison's idea was like, let's put down a bunch of DC power plants, like all over the place, like as common as probably as cell towers are nowadays, and provide DC power, have little nodes that provide direct current power. What Tesla wanted to do was to provide stations that were far outside of the city, and then to send alternating current in and use things that were called transformers to step up and step down the power as needed. And that's how we ended up doing it. So I think that's part of the reason why people say Tesla is greater than Edison. I think also because Tesla did a lot more things than Edison did, and a lot more creative things. He also has a lot of mystique associated with him. There's a lot of conspiracy theorists that really like Tesla, so be wary with what you read, because people will just straight up lie to you when you go find sources on the internet, right? So just be very careful what you read, and be sure that you're checking your sources, and more importantly, just be skeptical of what you read. But anyway, so that's where the Tesla from the Tesla automobiles company comes from, is from Nikola Tesla. It also happens to be the unit that we use for magnetism. And you'll notice we didn't give a unit to Edison. So perhaps the scientists who made these decisions kind of tended to agree that calling the magnetic field units Edison's was stupid, and instead they called them Teslas. All right. So, when we talk about magnetism, unfortunately, I can't, as I said, I can't write down an expression for the magnetic fields similar to what we did with point charges. I can't write B equal to KQ over R squared. That doesn't exist. What we can do is we can learn methods for finding magnetic fields. But we're going to have to learn about those in the next section. Because what we're going to do first is we're going to learn about the effect that magnetism has on two different things, on moving charges and on electric currents. So that's going to be the first thing that we're going to describe, because there's really no other way to talk about it until we actually develop what a magnetic field is and where it comes from. So that's what we're going to do, is we are going to investigate the force of a magnet or a magnetic field on charged particles and electric currents, or we'll say current carrying wires and loops and things like this. Okay. So in order to do this, I'm going to tell you some of the things we know about the way that a magnetic field can affect a charged particle. Okay. here's the actual result, but I'm just going to talk about what we know is all I'm going to do right now. I still want to move this stuff even farther down. We'll get to this stuff in a second. So what do we know about a charged particle and how it interacts with a magnetic field? So here's what we know. These are the experimental observations. You will see all of these when we do some labs in a little bit here. One of the labs we do is going to be all about what we're discussing right now. The experimental observations are this. One, if I have a magnet, okay, which obviously produces a magnetic field, okay, and I place a charged particle near it, okay, so I have a charged particle here. This particle will feel no force unless it moves. And it has to move in a very specific way to feel a force, okay? But I can say, to begin with, the particle will feel no force unless it moves, okay? So if it does move, okay, then when the particle moves, so we'll say when the particle has a velocity v, the force on the particle is perpendicular to the velocity of the particle and to the magnetic field. So when the particle has a velocity v, the force on the particle is perpendicular to both the velocity and the magnetic field. That is kind of weird, right? What I'm saying is, suppose that I have a North Pole magnet right here. So this is the North Pole of a magnet, and this is the South Pole. And I just draw on some field lines. Just to keep things simple, I'm just going to draw one field line right here. If I draw more field lines, it just gets really, really complicated, okay? So I'm just going to draw the one field line that extends straight up this way. But understand, there are field lines all over the place right here, okay? All going out like this. But we're not going to... It gets just way too complicated if I try to talk about that. Oh, there's a really good video for this. I should really just show you the video. Now let's go through the theory real quick, and then I'll show you the video. That's probably the best thing to do. All right, so now, let's say that I have... So this is magnetic field, okay? So that's magnetic field. Remember, magnetic field, electric field, they're different from each other. They're not the same thing. They have different units, but they're still vector fields. So if I draw a line like this, you understand that that could represent a magnetic field, right? All right, so we've got this magnetic field right here. So now if I take a charged particle, okay, let's say I have a charged particle and it's passing by this magnetic field line. And let's say the velocity of the particle is in this direction here, okay? What I just said was when the particle has a velocity v, the force on the particle is perpendicular to the velocity and the magnetic field. So I've got a velocity that goes this way. I've got a magnetic field that goes this way. I have to come up with a force vector that is perpendicular to both of them. Can anyone describe how I could do that? How could I find a third vector that's perpendicular to both of these? And I don't mean mathematically, I just mean geometrically. I don't want you to use, like, math terms. I mean, you can use some, but don't, like, I don't want to... Just want to talk about the geometry of this. I know that's a math word. It's either into the page or out of the page. Exactly. Exactly. Okay. So if I have a velocity this way, and I have a magnetic field that's up, I can basically create like an L like this, right? Where, I don't know if it's in the same direction as what you're seeing on the screen. Is my thumb pointing in the same direction as the V on your screen is? Very good. That's good. Because all this stuff is about... So do you understand that if I have an L with these two vectors, they make a plane, right? And the plane in this case is this plane right here. The plane of the page. So if I want a vector that is going to be perpendicular to both of them, it either has to point into the screen or it has to point out of the screen. Those are the only two possibilities. I'll tell you in this case that the force is going to point out of the screen if the particle's positive, but that's not important. So how can I draw that? Well, what we can do is we can create a standard where we say that if I draw a vector like this, this is a vector that points out of the page. Okay, and if I draw a vector like this represents a vector that points into page. And the way you're supposed to think about this is imagine there's an arrow, like an arrow with feathers on one side. If the arrow comes towards you, so towards you would be like that. then you would see the head of the arrow, the tip. That's what this one is right here for out of the page. And if the arrow was going away from you, so away from you would be like this, I think, and there's feathers on the arrow back here, then you would see the feathers. When it comes towards you, you see the head of the arrow. When it goes away from you, you see the feathers. So that's out of the page, into the page for vectors. So on my picture right here then, I'm going to tell you that it's going to point out of the page in this case. So that's the direction of what I'm going to call the magnetic force. And I'm going to label it F with a B subscript, okay? So FB means magnetic force. Okay? All right, so we know that when the particle has velocity v, the force on the particle is perpendicular to the velocity in the magnetic field. Okay? This would be true even if I take that velocity vector and I tilt it this way. Even if this velocity vector was going off this way, as we'll see in some examples, the force would still be in the same direction. Okay? Although it would be kind of smaller. All right? Other things that we can say is the size of the force is proportional to three things. They are the charge of the particle, the velocity of the particle, and the size of the magnetic field. So if we increase the charge, the force is going to be bigger. If we make the particle move faster, the force is going to be bigger. And if we increase the size of the magnetic field by going and grabbing a stronger magnet, the force will be bigger. Okay? Direct proportionality. The force is directly proportional to charge, velocity, magnetic field. And I think those are all the properties that are important before actually putting the equation on the board here. So the equation is right here. This is the magnetic force on a charged particle. It's a very important part of understanding magnetism. And what we do is, in order to ensure that the force is going to be perpendicular to both, this is seeable, right? We say the force, and this is for me, I never write things without putting subscripts on them. This would be FB for force, magnetic force, is equal to the charge of the particle times the particle's velocity cross products with the magnetic field. So this is V cross B. So we say QV cross B. QV cross B. The particle's charge shows up here. That means that if the particle's charge is negative, the force will point in the opposite direction, assuming the other three things are equal to each other, or the three things are the same. You do put the charge in here, is what I'm trying to say. If it's a negative charge, you put a negative sign on there. If it's positive charge, you put a positive sign on there. Okay? All right, so that's our equation. Force is equal to QV cross B. Those are the three things that go into it. Now, it's worth going through and refreshing what V cross B means. So I will do that briefly here. In order to define V cross B, what we have to do is to use the right-hand rule. You're going to be getting very good at this, and if you don't, then you're going to be a little bit lost sometimes, so this is worth your while to learn how to do this. Suppose that I have a velocity vector and it points this way. We're not going to worry about anything other than just the velocity vector and the magnetic field vector. I now place a magnetic field vector and it points this way, and I put them kind of like this, okay? From a numerical perspective, the cross product is simply found. If I want to find the magnitude of the cross product, you simply take charge times velocity times B, and then you multiply by the sign of the angle between the velocity and the magnetic field. Okay. When I write V without anything on it, I mean just magnitude here, and B, I mean just magnitude here. Okay. When you cross product a vector with a vector, you get another vector, by the way. That's why you have vector on the left side and vector on the right side here. Okay. What about the direction? In order to find the direction, I'm going to have you try to do this with me. And again, I don't know what's going to happen with the way things reverse on the screen and stuff like that. But if you take the fingers of your right hand and you point them in the direction of the velocity, like this, using your thumb kind of pointing directly into the hinge or the place where you can't see what I'm pointing at. This is the worst part about doing stuff on the internet. Can you all do this, though? Are you able to point your fingers in the direction of the velocity vector? Just do that. Okay. What you do to find the direction of the force vector is you rotate your fingers from V to B. So from here to here through the smallest possible angle, and then the direction your thumb points is the direction of the magnetic force. What direction would that be in this case? So it has to be your right hand. This is called the right hand rule, okay? Take your fingers of your right hand, point them along velocity, rotate them down to the magnetic field, and the direction your thumb points is the direction of the force. In this case, it's into the page. So what I'm going to do is right here at the vertex, I'm just going to say the magnetic force is into the page. That is the X with the circle in it, right? Like that, okay? Now, you're going to see all types of different examples of this, so I'm just going to start giving you examples of what's going to happen in your textbook, what you're going to start seeing. And I'm just going to ask you to guess what the direction of the force is, okay? Suppose that I tell you that I have a magnetic field that looks like this. You will see all kinds of stuff like this that show up in your homework. You need to get used to it. So I have a magnetic field. Does it point into the page or out of the page according to this picture here? What do these little X's represent? Into the page, exactly. Okay. Let's throw on here a velocity vector. So let's say that I have a particle, okay? And let's say that the velocity goes this way. And I tell you that as a positive particle, this absolutely matters that it's positive, okay? So this is a positive particle. So we have particle Q. It's a positively charged particle, okay? Positively charged particle. Now, if you want to find the direction of the force, do the same thing as before. Point your fingers in the direction of the velocity, okay? And you need to rotate them to the direction of the magnetic field. The magnetic field is into the page, right? So you rotate your fingers from velocity. So your fingers are pointing directly along the velocity vector. Imagine your middle finger just lines up directly with the velocity vector, right? And you rotate your fingers from there to the direction of the field, which is into the page. And you go from here to here through the shortest possible angle, which is about 90 degrees in this case. What direction does your thumb point? Up is not exactly right. Up and left is more correct. So now the force vector in this case, which I'll draw in red. Nope, didn't want me to do that. It wants to just, yeah, okay. The force vector in this case is going to point this way. Remember that one of the things that I stated, the very first thing that I said right here, when the particle has a velocity v, the force in the particle is perpendicular to velocity and magnetic field. Hopefully you can see that this vector, it's obviously perpendicular to velocity, right? You can see that one easily. But a vector drawn here is guaranteed to be perpendicular to the magnetic field because it's going into the page, right? Okay. All right, now, let's side by side to this one, let's do a negative particle, okay? If I have a negatively charged particle, okay, so here I'm going to put a negatively charged particle, and just to keep things really simple, let's say that it moves exactly in the same direction here, right? Now, to do a negative particle, you go through the same process. You point your fingers along the velocity, you wrap your fingers into the direction of the magnetic field, and you say, my force vector points this way, but it's a negative particle, so you need to multiply by a negative sign. What happens to a vector when I multiply by a negative sign? It flips the vector around by 180 degrees, which means that if I have a negatively charged particle, the force, right, is going to be this way. Exactly 180 degrees opposite of what the force on the original one would be. You'll understand? Negatively charged particles, you got to flip it around. This is something that is going to fool you, so be really careful. You're not going to use the left-hand rule, although it would work. Don't use it. Just remember one rule, and then when it's negative, just flip it. Okay. We could do more, but I want to mention something else here. I want to say something real quick here. What kind of trajectory would this particle take? Its velocity points this way, right? Its force is pointing kind of to the left relative to the direction it's going. So what would the trajectory of this particle be? Would it just keep going off in a straight line like this? Up. That's really vague, Evan. Come on, you can do better than that. Not just up. It's going to curve up, right? We could say that, I guess. I guess you could say that. The trajectory this is going to go on is going to kind of be like this, right? And the trajectory that the other one's going to go on is going to kind of be like this, right? So it turns out that this is actually how we identify if particles are positive or negative and we don't know. We stick them in a magnetic field where we know the direction of the magnetic field. We know the velocities of the particles, and that means the ones that curve left are positive, right? And the ones that curve right are negative. This is quite literally how we distinguish positive from negative particles. And because the size of the force is proportional to the charge, the bigger the charge is, the more curvature there's going to be. And the smaller the charge is, the less curvature there's going to be. As we'll learn more about that here in a little bit. But We'll go into detail about that calculation. Anyway, so being a particle physicist, this is a pretty important part of my studies in terms of determining charges of unknown particles. Okay, so here's some, boy, this thing got, like, what is it, stretched, I guess? There it goes. Okay, so here's a few things that your book mentions, and then we'll do an example problem. So, one thing that I didn't mention is that a charge moving parallel to a magnetic field will experience zero magnetic force. Hopefully you can see that from this equation here, okay? That if the velocity is parallel to the field, there is going to be no force, okay? And that's because the angle here would be, what would the angle be for the top line right here? If the velocity is to the right and the magnetic field is also pointing in the same direction, what would the angle be? 0. And then if the velocity is to the left and the magnetic field is to the right, the angle is 180. In both cases, the sine of 0 and the sine of 180 are 0. So, parallel to the fields, get no force. Here's a nice picture here where they have the velocity of the particle is in this direction here. The magnetic field's in this direction here. You should be able to verify for yourself that if you stick your fingers in the direction of the velocity, you rotate to B, your thumb points up. Right? And then here they have some information about how you do the right-hand rule, okay? And, you know, just to review, I already said it, but I'm going to review it here because it helps. The right-hand rule for the direction of the magnetic force on a positive charge in a magnetic field, see, it just says positive, right? Place the vectors V and B tail to tail. V, here, tail to tail, right? 2, imagine turning V towards B in the V minus B plane through the smaller angle. Okay, so imagine that this V could rotate towards B. The force acts along a line perpendicular to the VB plane. Curl the fingers of your right hand around this line in the same direction as you rotated V. Your thumb now points in the direction the force acts. That is to say, take your fingers, sometimes you have to rotate your body to do this, point them in the direction of V. In this picture, in my mind, the V is kind of coming out of the page like this, right? You go, V goes this way, and you think about V goes to B, and then you just do that, and your thumb points in the direction of the force. They give you another example here, where if the velocity was off in the 180-degree direction the other way, you'd say V cross B, thumb down is the force. Now, when I do this, it's really fast for me, and I can just generally do it in my head, but I'm always going to use my hand when I do it. I can look at this picture and be like V cross B and say it's down, just because I have a lot of experience doing this. Understand that it won't be so simple for you when you're doing your homework. You'll have to take some time to think about it, but as long as you practice it and try it every time just by using your right hand, you'll eventually figure this out. It's not really that complicated. In fact, it's a nice, helpful way to find this third vector. Okay, so there we go. That's what we know so far about the relationship between magnetism, electric charges, and velocity, and the force that they produce. Does anyone have any questions before we start looking at some examples? Ooh. Please ask if you do. Okay, so in case you ever forget what a Tesla is equal to, this is how you can figure out what the units are. In my equation right here, if I rearrange it, I made a mistake. If I rearrange it and solve for magnetic field, this is how you figure out what a Tesla is. The units of force are newtons. The units of Q are coulombs. The units of velocity are meters per second, but coulombs per second is amps, so a newton divided by a meter times an amp. That is what a Tesla is. Okay? So 1 Tesla, right, is equal to 1 Newton meter per amp. Newton per meter amp. Newton per meter amp. There we go. That's what a Tesla is. Notice that, I don't know if you remember this, but I think I told you at one point that amp is our new fundamental unit, right? So technically Newton is not a fundamental unit, but it's composed of fundamental units. So Tesla is not a new fundamental unit. It is directly related to the ampere. And this all goes back to the fact that this guy Ørsted discovered in 1820 that a magnet can be deflected by a current-carrying wire. Now, we're not quite to the understanding of what's happening there yet, but it does tell us that magnetism and electric current are related to each other, and eventually we'll show that magnetism comes from electric currents. Whoops. All right, so if there aren't any questions, we're going to do one. This is a super simple example, just designed to get you comfortable with the equations. So this is our equation, F equal to QV cross B. It says a beam of protons with Q equal to 1.6 times 10 to the negative 19 coulombs, that's the charge of the electron, also the charge of a proton, moves with a velocity of 3 times 10 to the 5th meters per second. So the velocity is 3 times 10 to the 5 meters per second through a uniform 2 Tesla magnetic field. So B, uniform field, so 2.0 Tesla, that's our magnetic field, directed along the positive z-axis. So we've got an x, y, and a z coming this way. The velocity of the particle is here, and the z-axis is this way, and that's the direction of the magnetic field. The velocity of each proton lies in the xz plane and is directed at 30 degrees to the positive z-axis. So the angle between velocity and B, velocity in the magnetic field, is 30. We want to find the force on the proton, the directions of V and B, blah, blah, blah. Okay. This is really easy to do, but I guess I'll try to show you 2 different ways, I guess. So method number 1, if I want to find the magnitude of the force, I can just say if I take the magnitude of the charge, I multiply the magnitude of the velocity, multiply by the magnitude of the magnetic field, and I multiply by the sine of the angle between them, which in this case should be 30 degrees. It has to be the angle between V and B, so be careful about that. It won't always be so simple as just looking at the picture. You'll have to think about it sometimes. And I plug everything in, so 1.6 times 10 to the negative 19 for the charge. For the velocity, we plug in the 3 times 10 to the 5. For the magnetic field, we throw in 2 Tesla. So it's just a normal calculation, right? Nothing special here. This is just like plugging numbers into a normal equation. Nothing new. Sine 30 is half, so it's going to cancel with this. So our answer is going to be 3 times 1.6, which is 5.4 maybe? No. What's 3 times 16? 48? 48. So 4.8, and then it's 10 to the negative 19 and 10 to the 5. So that's going to be 10 to the negative 14, right? And the units here, Teslas times coulombs times meter per second, is going to give me newtons. And that would be the magnitude of the force. But we also need to figure out the direction of the force. So what's the direction of the force? Can you all tell me? What would the direction of the force be in this case? Use your right-hand rule. Point your fingers in the direction of the velocity, rotate them towards B, and tell me what direction does it point? Down. Negative y direction, right? So if we really wanted to write this as a vector, what we could do is we could do 4.8 times 10 to the negative 14 newtons times negative j hat. Right? And again, it's because you do V cross B, your thumb points down. Hard for me to show that on the screen because it requires me to do this. V goes out, you rotate your fingers from V to B, your thumb points down. Okay, so verify for yourself that you get the same answer. Alrighty, so the next thing we want to do is to do this in a way where we just look at the equation and do it kind of using mathematics. Okay, so let me make a little room here so we can keep this all on the same page. So now, instead, another method to do this. Okay, so alternate method. Let's use red. So the other way we could do this is we could say that velocity vector, v, I could write it in unit vector notation as well, right? What would it be? Well, this velocity vector has like a component that goes this way and a component that goes this way, right? And since I know that angle is 30 degrees, I know that this angle is 30 degrees right here too, right there, right? In fact, we'll just label it as phi. So this angle is the same angle right there, which means that this side over here is going to be v times the, what, sine of phi? And this side over here is going to be v times the cosine of phi, right? So what we could do is we could say our velocity is equal to v sine phi multiplied by I hat plus It's positive, right? V cosine phi. And then what should I multiply V cosine phi by? Should I multiply it by J hat or K hat? And it should be positive or negative. V cosine phi right here. I put J hat or K hat here. Okay, a bunch of different people are saying different things. Notice that the x direction is this way. The y direction is up, right? The velocity vector v is in the xz plane, right? And I've written down the x component is v sine phi, and I multiplied that by I hat. The z component is v cosine phi, so we have to multiply that by k hat, because this is the one that's parallel to the z-axis, right? Okay, so this would give us our velocity vector, right? What about our magnetic field vector? Well, that's easy. The magnetic field points only in the z direction, right? So we can say magnetic field then is going to be 2 Tesla times positive k hat, right? And now what we need to do is we have to do q v cross b, right? Equals fb. So what we're going to get is q, which was 1.6, times the velocity. So now for the velocity, we'll put this whole thing in here. V was 3 times 10 to the 5th, right? So this is going to be 3 sine of 30 I hat plus 3 cosine of 30 j hat multiplied by times 10 to the 5 meters per second. So I basically just pulled out the that thing. And then it's QV cross B, right? This is going to be complicated if I leave it like that. We're going to make that a dot. Okay, let's just do that. And we have to cross product this with 2 Tesla times K hat. Right? Okay. So let's think about what we're going to get out of this. We have an I hat term crossed with a K hat term. And we have, whoops, I wrote it down wrong. My bad. That was another K. That's a K hat as well. So we have an I hat crossed with K hat, right? If you look at those 3 things right there, we have to perform that operation. I cross K. But we also have a K crossed with K, right? So I don't know if you all remember this stuff, but what do you get if you do I cross J? Yeah, I cross J, you get K. And what happens when we flip it? What do you get if you do J cross I? You get negative K. That tells you one of the properties of the cross product, which is that if you reverse a cross product, you get the negative sign, right? Like if I tell you that A cross B is equal to C, you know for a fact that B cross A is equal to negative C, right? It's a property of the cross product. Okay. So I cross J is K. If you can't figure that out why that's the case, point your fingers in the direction of I on my little coordinate system right here. Rotate them to J and your thumb points in the positive K direction, right? What about the other ones? What about like I cross I? What does that one give you? You get 0. Another property of the cross product is if I take A cross A, any vector crossed with itself is automatically equal to 0. We'll use this property much in the future. Okay. Now we need one more. There's a total of 9 of these, but I cross I, J cross J, and K cross K are 0. The one we want to look at is I cross K. What is I cross K going to be? Is it going to be negative J? Is it going to be positive J? What's it going to be? Take a time to think about it. Take your fingers and point them in the I direction, and then rotate them to the K direction, and your thumb should point in the negative J hat direction. Okay? Alright, let's solve this problem, then I'll teach you some rules real quick about how you can do these things quickly without having to think too much about them. Okay, so that means our magnetic force is going to be equal to, all we need to worry about is this times this times this times this. And then we have an I cross K in there, so that's what I'm going to do. We are going to get the exact same answer as we got before. It's the same multiplication, so I'm not going to go through it again. 4.8 times 10 to the negative 14 newtons, right? And we'll also have on here an I cross k, which we saw above is just equal to negative j hat, and we get the exact same answer. You can do this either way that you want to. It should work both ways. It's really just up to you which one you prefer, right? But you can see that this is the same as the answer we got right here. Okay? And of course, there's also a k cross k term, but as we said above, I cross I, j cross j, those are all equal to 0, so we don't need to multiply that out. Does anyone have any questions? Pretty easy problem. Now, as an aside, I want to mention some things here. If you take the I, j, k vectors and you write them down like this, just write them down as a like a list like this, okay? If you do I cross j, you get k. If you do k cross I, you get j. If you do j cross k, you get I. It turns out that if you go in order, okay, if you go in alphabetical order, I cross j, automatically you get k, okay? But if you go out of order, anytime you go backwards, so if I want to do j cross I, you see that I have to go backwards in this list here. If I do k cross j, I have to go backwards in this list. That's where you get the negative sign, okay? So as long as you go in alphabetical order, where the alphabetical order is cyclical, right? K, I, j, k, right? Then you'll always get the right answer for these. So let's just go through each of these. So I cross j is k, right? J cross k is I. You see how I'm getting that? Because for j cross k, all I do, I can't undo as much. I just go from j cross k and it's the next one, which is I. Okay? We can keep going. K cross I, what's that equal to? Can you guys tell me really quickly? Don't think about it. Just use the kind of method that I just said. K cross I is j. Yeah, exactly. Okay, so again, as long as you're going forwards, you're fine. Now, if you skip one, skipping one is not allowed. So you have to make sure you go to adjacent ones, all right? So what happens when we go backwards? So if we go backwards, if I do k cross j, I get negative I. It's the process of reversing the order, okay? If I do, what's next? J cross I. Should be whatever's next here, but it should be negative, so that's negative k. And if you do, what's left? I cross k? Yeah. I cross k is negative j. Does that help you all? I don't know. I hope it does. It can be very time consuming to always like try to look at the picture right here and verify. That being said, you should be able to do both. You should be able to visually understand why I cross j is k by using the right hand rule, right? But you should also be able to do this. This is just way easier. And it's what I do. When I ask people, hey, what's I cross j? I already know it's k because it's I, j, k. It's alphabetical order. And then when I do something like k cross j, I think, wait, what comes first in the alphabet, k or j? The answer is j. So this is going to be negative. That's it. And if you think a little bit about it, it should be pretty obvious why it works. Anyway, so, I mean, you really just need to know these properties, and you can prove why this process here works. All right, we're going to take a break. We'll take a 10-minute break till 2:33, and that's that for the first part of the class.